Good day, grade 12s. This is our fourth lesson in our series on work, energy and power. In this lesson, we're going to stand still a bit at the force or the work being done by gravitational force on an incline. But before we do that, let's quickly mark the question or the problem that we had in the previous video. If you have not done that problem yet, please go and sit down and first do the problem. Remember, physical science, as I always say, is not a spectator sport. It's about developing cognitive functions. And you have to sit and struggle with these problems in order to develop your brain. So just watching the videos probably won't help. I've been really encouraged by learners that send me photographs of their worked out problems, how they marked it, where they picked up their mistakes, how they corrected thinking patterns. That's what it's all about. So I hope you are part of those. Okay, let's look at this problem. A learner throws a rigid board in such a way that it reaches the top of a 3-meter wall as shown in the sketch. He drags a 5-kilogram crate with a force of 50 Newton at a constant velocity to the top of the board. The problem with this question was that we had no theta here, and in all the previous questions they gave us this incline and this time they didn't. But what they did give us is this distance of 4 meters and that distance of 3 meters. So let's see how we go about doing this problem. Our equation for work done by our gravitational force will be equal to the gravitational force times the distance which this force travels times cos of the angle between the force and the direction that this object is traveling. So here I have theta in my sketch. So this is the angle that I'm looking for. Okay. So let's pop into the information that we have. We know the gravitational force is equal to the mass times gravitational acceleration. The mass of this block is 5 kilograms. So in the place of m, I can put in 5. In the place of g, I can put in 9.8. So F equals mg, Fg. There we go. But that is the only information that we have in our sketch. Now let's quickly have a look at this situation right over here. Okay. I want to know something about this little red angle. So for the sake of this question, what I'm going to do is I'm still going to call this, or I'm going to name this red angle in terms of this angle, because that's the one that I want to calculate. Now, what is the relationship between this small little red angle here and the entire theta that I need? Well, theta is just equal to 90 degrees. You can see between horizontal and vertical, it's 90 degrees. 90 degrees plus the little red angle. So the little red angle will be equal to theta, which is the entire angle, minus the 90 degrees. And that's where I got this value from at the bottom. Tan of theta minus 90, which is the red angle over here, will then be equal to the opposite side divided by the adjacent side. And that is equal to 3/4. Let's just wait for the black bar to disappear. There we go. So tan of theta minus 19, which is the red angle in my sketch, will be equal to the opposite side 3/4. And if I go and calculate that, that means the inverse function of 3/4 is going to be equal to theta, which is the big angle here, minus 90. It's going to be equal to this angle. Okay, and this I calculate on my calculator using the inverse function. And so I get theta minus 90 is equal to 36. So now I know this little angle over here is 36,87 degrees, which means my entire angle, which is the theta that I'm looking for over here, is going to be equal to 126,87 degrees. Great. So I've got this value, I've got the force, I've got the angle. I only need the distance that this thing is traveling. And for that, I'm going to apply maths again. But this time I'm going to use Pythagoras statement. That's right. This is a right angle triangle. So I know this side squared plus this side squared will give me that side squared. So x squared, let's call this one x, is going to be equal to 4 squared, which is 16, plus 3 squared, which is 9. 16 plus 9 will give me 25. And the square root of 25 is 5. So I just worked out that my x over here is going to be 5, the distance that it travels, so I can put in all those values. and calculate 5 times 9,8, which is my force, times 5, which is the distance that it's traveling, cos of the angle between them. And if I work all of that out, I get negative 147 joule. What does this negative sign mean again? Remember, work done is a scalar. So the negative sign has nothing to do with direction, because work does not have a direction. There are many other scalars that also have negative values that has nothing to do with vectors or direction. An example of this, for instance, is temperature. You get a temperature of minus 5 degrees Celsius, which means it's 5 degrees below zero. It's got nothing to do with a direction. In the same way, this negative sign gives us information about the relationship between the force applied and the direction in which this thing is traveling. And the negative sign is just telling us that the angle between these two will be greater than 90 degrees. Okay, I'm going to do the same problem, but using mathematics and a bit more advanced mathematics, and you will see this is going to be such an elegant solution. Okay, again, before I start, I want to look at something about this. I want to start at this angle over here. In my previous sketch, this was my little red angle. Okay, and I want to write it in terms of the theta. Theta I'm going to keep as the angle between the force that's applied and the direction which I'm moving. But this little small angle that is equal to the big angle minus 90. Sin of this, or sine of this angle, remember sine is opposite over hypotenuse. So that is going to be equal to 3 over delta x. Now, to apply a little bit of more mathematics, I know sine of theta minus x is the same as, I just take out the negative sign, same as sine of minus 90 minus x. There's my negative 90, and a negative times negative will give me a positive sign. So I'm just changing these two around, so that I know that sine of 90 minus x is the same as minus sine, or sine of theta minus 90, is going to be equal to minus sine of 90 minus theta. This you've done in maths. This is just pure mathematics. And sine of 90 minus theta is going to be equal to minus cos of theta. So what have I seen now? I've seen that sine of this small angle over here is going to be the same as negative cos of the big angle over here. And that should get some of you sitting up straight a bit. Because where have you seen cos of theta before? You know that is something that they use in the work equation. And that is what I'm going to substitute in. So let's look at my work equation. The work done by the gravitational force is going to be equal to the gravitational force times the distance that it's traveling, which I'm calling delta x, cos of theta. But now I've just worked out that cos of theta, cos of theta, there I have it, is equal to minus 3 over delta x. That is exactly what I used here, when I used my math to get this relationship. And now you can see these two will actually cancel out because they're the same value. I multiply by delta x and divide by delta x. So my solution at the end of the day will just be 5, which is my mass, times gravitational acceleration, times the distance, negative of the distance, the perpendicular distance that this thing is moving. And I still get the same answer, but with much less steps and a much more elegant solution. I think quite a number of you will be a little bit scared of this solution and think, whoa, I would have never thought of this. And you're quite right. This is an advanced solution. But do take note, knowing your maths very well, knowing your trigonometry and identities, knowing your geometry in general, understanding the properties of triangles and so on, really comes in handy when we work with physical science. So it's worthwhile to know your maths. Let's look at the second part of this problem. Calculate the work done by the friction force acting on the board. Now, one of the pieces of or clue or tips that we have in his sum is that he tells us he drags a 5 kilogram crate with a crate of 15 newtons at a constant velocity. This constant velocity tells us that the resultant force acting on this object must be 0. If the resultant force is 0, it means the resultant work, which is the sum of the work of all the different forces, must also be 0. So I know this to be true. Okay, so let's just first have a quick look of what are the forces acting on the system. We have our normal force, applied force, the gravitational force, and the frictional force. And again, I color-coded them over here so that you understand about which force I'm talking all the time. Many times before, we saw that the work done by the normal force on an incline is going to be 0 because the direction of motion and the force is exactly 90 degrees on top of each other. The angle between them and cos of 90 is 0. So immediately I can write down the work done by the normal force is 0. The work done by the frictional force, that's the one we need to calculate. Then I know the work done by the applied force is going to be my applied force times this distance that this thing is moving, cos of the angle between the force and the direction. But now you can see the force and direction is the force is in the direction, so that angle is going to be 0. And the work done by the gravitational force I calculated in the previous sum. Also, when I calculated in the previous sum, I used this 4 meters of the bore down here and the 3 meters up there, and I used Pythagoras to calculate that this angle, or this distance x, is equal to 3 squared plus 4 squared, the square root of that. That gave me that this distance over here is 5. So as far as my applied force is concerned, I can put in the values of my force, which is 15 newtons, times the distance that it's traveling, which is this distance, which I calculated using Pythagoras in the previous sum, minus the 147, which I also calculated in the previous sum, and then I get the work done by the friction force is minus 103 joule. Does this make sense? Of course it does, because the direction of motion is going up the incline, the frictional force is going down the incline. The angle between those two are more than 90 degrees, so my work done must be a negative number. I'm going to look a bit closely about this whole issue of gravitational work, the work being done by the gravitational force on an incline. So I'm looking at a very, very general example. In this example, I have a general distance of height, general height, h, and I have any incline that has a slope with a distance of x, and I've got a mass going down there, and the incline, the angle for my incline is just called phi. So bear with me. I'm now going to apply pure maths and show you something quite handy as far as the work done by the gravitational force is concerned. But we have to apply a little bit of maths and do a little bit of a general example for this. Okay, so the amount of work done by the gravitational force is given by the force times the distance that this force travels, cos of the angle between the force and the direction that it travels. So it will be this angle over here, which is theta. Okay, so that angle there, I've got my angle theta. I want to write that angle in terms of phi at the bottom. Now to do that, I'm going to have a look at this little purple triangle over here. If this angle is phi and this angle is 90 degrees, how do I know that this angle is 90 degrees? Because my gravitational force is going directly vertically downwards, and this is my horizontal, and the angle between horizontal and vertical is always 90 degrees. Then from grade 9 maths, you should remember that the exterior angle of a triangle is equal to the sum of the opposite two interior angles. So these two, phi plus 90, must give me that angle. Okay, so let's put in, remember what was this angle again? It's the angle between the force and the direction of motion, so it's this theta. Theta, I know here in terms of phi, which is the small angle over here, is going to be 90 plus x in this situation right here. So I substitute that into my equation. Okay, now let's look a bit at this cos of 90 plus phi. If you apply your trigonometry identities, then you know that cos of 90 plus phi is equal to minus sine of phi. Where do I get that again? Okay, let's look at this identity from maths, from pure maths. I think most of you should remember this. Cos of A plus B is cos A cos B minus sin A sin B. Now in this case my A is 90 degrees and my B is phi. So if I put in those values, then I know cos of 90 is 0. So this entire first term becomes 0. And sine of 90 is equal to 1. So this whole thing becomes minus sine of phi. So that's how I can say that this thing works. So where did I start it out with? Let's just quickly summarize. I got my angle theta in terms of phi, which is just this small angle over here. That using basic maths. And then I plug that into this equation and I simplified cos of 90 plus phi so that it became sine of phi or minus sine of phi. Now let's continue. And now with sine of phi, I'm going to look at this big blue triangle. There's phi for the big blue triangle. H is my opposite side. And x is going to be my hypotenuse side. So I know sine of theta is opposite divided by hypotenuse. So that is just going to be h divided by x. So over here, instead of sine of theta, I can actually substitute h over x. And what does that give me? Now I have here that I multiply by x and divide by x so the two x's can actually cancel. And I'm left with the work done by the gravitational force for a block that's moving uphill is minus mass times gravitational acceleration times the height of that incline, the vertical height. Does the negative sign make sense? Yes, it does, because the angle between the force applied and the direction of motion is more than 90 degrees. Oh yes, I still need a unit here, right? So let's add that. That's more like it. Okay, now we just looked at a block that I take up an incline. So now let's look at another situation where a block is sliding down the incline and I just want to know what is the work done by the gravitational force. Okay, now in this case the angle between the direction of motion and the force applied is this one. Again, I'm going to call this angle at the bottom phi. So I want this angle, which is theta, in my work equation, right? That angle, the green angle there. I'm just going to see what this is in terms of phi. Now, how did I get to 90 minus theta? Okay, again, if you look at the outside triangle over here, then I know this top angle must be equal to 90 minus phi. How do I know that? Because three angles of a triangle must add up to 180 degrees. So this one plus this one plus this one must give me 180 degrees. So 180 minus 90 minus phi will be that one. 180 minus 90 is 90 minus phi. So I know this angle over here must be 90 minus phi. And these two angles are similar because these two lines are parallel. So I know this angle is also 90 minus phi. That's how I got that angle. So I can substitute this into my equation just so that I have this angle in terms of the incline. And then I have my gravitational force cos of 90 minus phi. And now I want to simplify cos of 90 minus phi, and I use my trigonometry identities to do that. From my trigonometry identities, I know that cos of 90 minus phi is equal to sin of phi. If you can't remember how I know that, let's just apply this identity just as a measure of revision for you as well. Cos of A minus B equals cos A cos B plus sin A sin B. These are identities that you need to know off by heart. Therefore, if I just substitute the A and the B with 90 and cos, then I have A is equal, cos of 90 plus theta is equal to cos 90 cos theta plus sin 90 sin theta. We know cos of 90 is equal to 0, so this whole term becomes 0. And we know sin of 90 is equal to 1, so this whole 0 becomes sine of 1. So now I know cos of 90 minus phi is just equal to sine of phi, and I can substitute that into my equation. But I also know something else about sine, about phi. If I look at this big triangle on the outside, there's phi. Sine of phi is equal to opposite over hypotenuse. This identity that I have this underneath. So instead of sine of phi, I can write h over x. And again, multiply by x and divide by x means that my x's can cancel. So I know the work done by the gravitational force for an object moving down a plane is just going to be equal to the mass times the gravitational acceleration times the vertical height of that object. This tells us something quite significantly. Can you see that this gravitational force is not really dependent on x? So this will tell me that if I push up a block on this incline and a different block on this incline, the amount of work done by the gravitational force for each case will be exactly the same, and for both of them it will have the magnitude of mass times height times gravitational acceleration. If I slide the block down, then the work done will be positive because the angle and the direction of the force that's applied is less than 90 degrees. And if I slide the block up, then this work will be a negative number. But the magnitude will be mass times gravitational acceleration times height. This was a little bit of hard maths. So I want to encourage you. I'm not going to give a homework sum on the end of this because this is a strictly theoretical lesson. But what I do want you to do is either tell somebody at home, your mother or your smaller brother and sister, or even to yourself in the mirror, sit down and explain to yourself or to whoever is prepared to listen why the work done by the gravitational force is equal to the mass times the gravitational force times the vertical height of a specific incline. Try to do all the calculations. Start from the very beginning where you only have this h there. You can identify the angle phi there and your mass with your gravitational acceleration. And from there, show how you derive that the work done by your gravitational force will give you this amount. Practice this a few times before you continue. Good luck.